Okay, honors physics. I'm gonna try doing a short lecture video that I'm gonna post alongside the reading assignment. I probably don't really need to tell you this in the video because you've already read the assignment post, but whatever. The reading assignment is about inclined planes and the way you can analyze forces for objects that are on a tilted surface, like a ramp, instead of on a flat surface, or just sort of like abstractly with, two-dimensional forces involved. So what I'm going to do is sketch the situation for you. I've got a ramp, and I'm going to put a block on that ramp. And to the side, I'm going to make a horizontal version just for the sake of you remembering. If I have this horizontal surface and I want to think about the forces involved, it's just going to be force of gravity, which I know has a magnitude mg. And then the reason the block doesn't accelerate is because the surface is holding it in place. And we call that force normal force. And again, if the acceleration of the block is 0, then those two forces have the same magnitude, and that would be it for the diagram. But the thing to keep in mind about the normal force is that it is normal. This word normal means perpendicular. So if I put the same block on the tilted ramp instead, the normal force has to stay normal to the surface. So the normal force can't go up like that, because that wouldn't be perpendicular to the surface. Instead, the normal force points this way so that it's still perpendicular. Now the force of gravity naturally points straight down, because that's the direction towards the Earth, the center of the Earth. So if you have an object on a tilted surface, the force diagram is like intrinsically going to be two-dimensional in nature. The vectors, you're going to have at least these two vectors, and they will not be on the same axis. They're going to be at some diagonal with respect to each other. So if I fill in some additional information, I'm going to name this angle down here alpha. I try to avoid using theta for the inclination of the ramp because I prefer to preserve the name theta for that unit circle style angle, the angle that comes counterclockwise from the positive x-axis, that angle theta. And this angle that I just labeled isn't measured that way. So I'm going to call it alpha for now. And the diagram that I've got right now, this is the simplest possible force diagram for an object on a ramp. I have to have gravity, and there has to be normal force from the ramp. Now, you can absolutely have other forces present as well, and we're going to see some of that. Frequently, friction is going to be involved. Like, if I were to put something on a tilted surface and it just sat there without sliding, the only reason that it wouldn't slide is if there's friction holding it in place. A lot of the physics problems about ramps also involve people like pushing things uphill or using a rope to pull uphill or downhill and various thrilling things like that. And I'll show you a couple of examples of that sort of thing. But most of the time, the additional forces that are present are going to be along the direction of the ramp itself. So you might have forces going uphill, you might have forces going downhill, but you're not usually going to have, say, a force which is horizontal. You could, but usually the problems aren't written that way. If you were actually pushing something up or down a ramp, you probably wouldn't apply a horizontal force. You would probably apply parallel to the ramp surface. So rather than setting up a reference frame like this, with the x direction being horizontal and the y direction being vertical, it is convenient when you're doing ramp problems to instead make the reference frame tilted so that it matches the ramp. So I have one axis which is parallel to the ramp surface. Usually we call that one x. And then there's another axis which is perpendicular or normal to the ramp, and we usually call that one y. So I'm going to label those. And at the moment that seems maybe arbitrary, possibly even confusing, because with a normal reference frame, the force of gravity points in the negative y direction, and the normal force is on a diagonal. With this new reference frame that I've just drawn, the normal force points along the positive y-axis, but the force of gravity is diagonal. So, like, what's the point of switching? I still have one diagonal vector and one vector that lies on the axis. But, for example, even if there's no other forces in the problem, I know that any acceleration the block might have is going to be parallel to the ramp surface. There's no way, if I just put a block on this frictionless ramp, it's not going to accelerate like up into the sky off of the ramp, or down into the surface of the ramp. It's not going to like burrow through. The acceleration is going to be along the ramp direction, either uphill or downhill. And that is what makes this more convenient. Also, like I said, most of the forces, in addition to these two, most of the other forces you see are going to be parallel to the ramp. But if you know the direction of the acceleration ahead of time, lining up your reference system with that acceleration is convenient. And you might remember that from the two-dimensional problems that you've done, because with the two-dimensional problems that you've done so far, in several of them, the acceleration had both x and y components. So you have to do a lot more math that way. But if you set up your reference frame so that the acceleration is only in one direction, only along one axis, that's going to save you a lot of effort in the long run. So, thing to keep in mind here, I'm going to move my FG label out of the way because I need to put something else in that space. Given the reference frame I've drawn, like I said, the normal force points in the positive y direction because it goes up away from the ramp. But the gravitational force, the weight, that is a diagonal force according to this reference frame. And so what I want to do is sketch in the components of the weight to help me think about how to set up any math that I need to do. And again, I want to emphasize that the x direction is parallel to the ramp, whereas the y direction is perpendicular to the ramp. That looks really small, I'm sorry. I just wrote parallel and perpendicular. So what I need to do is break the weight vector into a part that's parallel to the ramp and a part that's perpendicular to the ramp. So what that's roughly going to look like is a perpendicular component like this and a parallel component like this. So I'm going to draw in red to distinguish my components from the original vector. But those are the components that I need. There's a right angle between them. So this makes a right triangle, just like the components for any vector make a right triangle. But the weird part about this triangle is that, again, you kind of have to like tilt your entire perspective in order for it to look normal. I shouldn't use the word normal like that, for it to look what you're used to. So this side here, that's the y component, because the y direction is perpendicular to the ramp. And this one here is the x component. So now what I need to do is figure out which one of them goes with sine and which one of them goes with cosine. Usually, if you are measuring your angles like you would on a unit circle, you don't have to think about it, and you can just say cosine for x and sine for y. But the only angle that's defined in the problem right now is the angle theta at the bottom of the ramp. And hopefully you can believe me, just based on how the diagram looks, that that angle alpha appears up here in the top part of my little triangle for the components. One way you could try visualizing that is if you were to imagine a case where the angle theta was, or alpha, where the angle alpha is really small. So suppose I make like an example like this, where alpha is only like 10 degrees or something. If I try to duplicate what I was just doing, here's the FG. I need to draw a component that's perpendicular to the ramp. So that's going to be like this. And then I need a component that's parallel to the ramp, which is like that. And by exaggerating this where the angle is really small, it becomes pretty obvious that this angle up here is the one that matches the ramp's inclination. I have like a whole geometric proof of this that a student asked me to prove it to them my first year at AMSA. So if anyone really wants to see the proof, that would make your geometry teachers proud. I hope I have that available, but hopefully the example with the small angle makes it at least plausible to you. So anyway, the angle alpha is at that top corner of the triangle. And so, for example, the y component, again, the y component is this one, that is adjacent to the angle alpha, which means that the y component is going to be FG times cosine alpha, whereas the x component is going to be FG sine alpha, because that's the opposite side from the angle alpha. So this is one of the confusion points for most students when they're learning this, because up until now you've usually been able to rely on cosine x and sine for y, and it's reversed here. If it really, really bothers you that it's reversed, there's a way around it, but I feel like it is worse than just remembering that it's reversed, which is that I'm going to use another color here. This is in blue. That's a set of axes there. The positive x direction is going downhill. So that angle theta, the way I would measure theta for a unit circle, goes like that. So the angle theta is 270 plus the angle alpha. So if you really want to use theta so that cosine is always x and sine is always y, You can, you just have to make sure you're actually using the number for the angle theta. And that would be a weird angle to report about a ramp. If I want to tell you how steep a ramp is, I'm going to be telling you that angle theta, or alpha. I'm going to be telling you the angle alpha that's down at the bottom, because this is the angle that makes sense to talk about. If you want to do your old style calculations for the components, you just have to add 270 to it, and then you can use the old rules. But frankly, I think it's easier to just forget about all of that and either just remember, oh, on a ramp I have to swap them, or you could actually draw the triangle for yourself and think through it. There's one other warning I want to give you. I'm going to get rid of this other diagram, which is that a very frequent error that I see, here's another version, very frequent error that I see when students make the components is that they draw the triangle this way. And I think the reason they do that is because they're used to the components for a vector having a vertical part and a horizontal part. And if I draw in those two sides, there is indeed a vertical part and a horizontal part. But the vector that's supposed to be the hypotenuse, FG, is supposed to be the hypotenuse. It's not. And the triangle that I just drew, this is the hypotenuse. And the two so-called components that I drew in red, they're not perpendicular to each other, which means they're not really the components of the vector. The components have to be perpendicular to each other. So this is bad, no good. Do not draw your triangle that way. You've got to make sure that the components are actually perpendicular. Okay, so I'm going to get rid of that since it's bad. Okay, so in this very simple case where there's no extra forces, how would I figure out the acceleration, for example, of the block? Well, it's going to have to be in the x direction. I know that if the only thing that's going on is that I put a block on a frictionless ramp, it's going to slide downhill. So I'm going to start by trying to write forces in the x direction, since I know that that's the direction the acceleration is going to be in. So I know that ma has to equal sigma f. For now, I'm not going to put any numbers on it. But if I think about the sigma f, and remember I am doing the x direction specifically, so what I'm supposed to put in my sum is the x components of every force. Well, there's only two forces in the problem. There's the normal force, but that one doesn't have an x component because I set up my coordinate system in a way that the normal force points in the y direction only. The other force is Fg, and Fg does have an x component, which is this side down here. And I figured out from the geometry that that is Fg sine alpha. And Fg is mass times g. So ma equals mg sine theta, which means that the acceleration on a frictionless ramp, whoops, I need my g in there. The acceleration on a frictionless ramp should be g times sine alpha. Now, stop and think for a minute whether that makes any sense. A flat or horizontal surface has an alpha of 0. If I were to like gradually lower the ramp so that alpha got smaller and smaller, The ramp would become horizontal when alpha was 0. Sine of 0 is 0. So if the angle alpha is 0, my answer here tells me that the acceleration should be g times 0. That makes sense. If I were to make the ramp steeper and steeper until the angle alpha became 90 degrees, sine of 90 is 1. And so that would tell me that the acceleration was equal to g. That also makes sense, because if the ramp is completely vertical, then the ramp doesn't actually support the block anymore, and it should be in free fall. And so g is the acceleration I would expect in that case. So, frictionless ramp with no other forces, pretty easy. Okay, let me do an example that has some extra stuff in it. I'm going to do one with friction, I suppose. So I'm going to start the sketch again. Why don't I turn them? I'm going to turn the triangle around just to keep things interesting. That was a bad triangle. Okay. Here's my block near the top. I know there's going to be a normal force. I know there's going to be gravity. I know that the gravity has components like this. So this one in the x direction is mg sine alpha. The one in the y direction is mg cosine alpha. The angle alpha is the slope of the ramp. So let's say that there's some friction this time. I'm going to say that the block is sliding downhill, but there's friction present. So I'm going to draw some little speed lines coming off of the block so you know that it is moving downhill. It's moving to the left. And while it moves to the left, the force of friction is pointing uphill. This is kinetic friction, since the block is in motion. And just to be safe, I'm going to sketch in my reference frame. I still want the x direction to be parallel to the ramp, and I still want the y direction to be perpendicular to the ramp. Notice that since I've flipped the triangle around, this time downhill is negative x, whereas in my first example, downhill was positive x. That doesn't really matter that much, but depending on which way you draw it, or which way it's drawn for you, that can vary. So, I am gonna, what I want to do is figure out the acceleration. So, if I start the way I did last time with the x direction, you know, ma sub x is sigma fx, and the forces in the x direction, this time there are 2 of those. I have the x component of the gravity, which points in the negative x direction, and I also have this force of friction, which points in the positive x direction. So I've got minus mg sine alpha plus ffk. And force of friction has a magic formula. The magic formula for kinetic friction is mu k times Fn. So if I want to find the acceleration, I would just need to know what the normal force is. But unlike when you have a horizontal surface, the normal force is not equal to the weight. And I can show you that if I look at forces in the y direction. So I'm going to write out a statement for y. It occurs to me that I maybe should have addressed this earlier in the video, but whatever. All in one take. So if you look in the y direction, there are two forces present. There's the normal force, which points directly in the positive y direction, and then there's the y component of the weight, which is mg cosine alpha. On a horizontal surface, it would just be mg. You wouldn't have to throw in a trig function. So the forces side of this equation looks like Fn minus mg cos alpha. And I know that the block does not accelerate in the y direction. Again, this goes back to my choice of reference frames. Because I set up the coordinate system the way I did, I know the acceleration is only in the x direction. So the left-hand side is equal to 0. 0 equals Fn minus mg cos alpha. Therefore, the normal force is equal to mg cos alpha. So if I stick that into the x direction, conveniently, there is a mass in each term again, so that's nice. And the acceleration this time is negative g sine alpha plus, I should put a k subscript on my mu, sorry about that, plus mu k g cosine alpha. So if it were a frictionless ramp, like in my first example, that would basically mean that mu k was 0, and so that term would go away, and then I would have the same result from before. There's a minus sign this time, but that's because I flipped the ramp around. So the acceleration is downhill. It's in the negative x direction in this example. But if friction is present, then the magnitude of the acceleration is going to be less. Instead of having this full negative g sine theta, whatever number that is, I have a positive term that comes from the friction, and so the magnitude of the acceleration is going to be smaller. And again, that makes sense, because if there's friction, then it shouldn't slide down as fast. Now, I have a feeling I've already been talking for probably, oh, I can see I've been talking for half an hour. So I'm going to do a very fast final example that includes somebody pushing, force gravity, force normal. Let's say that a person is pushing uphill. I'll call that FP for push. Still need those components. I'm going to use some shorthand here, so the horizontal part is the sine part. I shouldn't say horizontal. The parallel part is the sine part, and the perpendicular part is the cosine. And let's put some numbers on it. Students like numbers, right? Let's say the mass is 50 kilograms. Let's say that the angle alpha is 20 degrees. And let's say that the person pushing is, I want to make sure it's big enough to go uphill. So let's say it's like 300 newtons. I'm pretty sure that'll be big enough. Okay. So in the y direction, I know that MAY equals Fn minus mg cosine alpha. And I know that the acceleration in the y direction is 0. So therefore Fn is mg cosine alpha. I said I was going to do this with numbers. The mass was 50, g is 9.8, cosine of 20 degrees. So I'll calculate a number for that. Normal force is 460.45 newtons. Oh wow, I wrote that really big, didn't I? Okay, x direction. MAX, still legible. In the x direction, I've got the push. That push is in the negative x direction. If I want to keep my coordinate system, arranged as usual. So there is the push, which is going to be negative 300. And then there is the parallel component of the gravity. I'm going to have to squeeze that in underneath, which would be mg sine alpha. Mass is 50, g is 9.8, and sine 20. I'm going to go ahead and erase that mass and just put 50 over there also. So that's what I've got going on in the x direction. Notice that turns out I didn't actually need to find the normal force this time. Since this was a frictionless problem, I said, that means that the acceleration actually has nothing to do with the normal force. So if you're doing a problem that is frictionless, typically you're going to be able to ignore the y direction completely, because the only thing you ever really get from the y direction is the normal force, and you don't need it here. But if you do have friction, you usually want to do the y direction first. So AX is going to be negative 300 over 50 plus 9.8 sine 20. So that's negative 6 plus 9.8 times sine 20. When I punch that in, I get an acceleration of negative 2.65. So the minus sign on that answer tells me that, yes, indeed, it is accelerating uphill. So it's getting faster while it moves uphill. If I had ended up with a positive number, that would mean that the person isn't pushing hard enough to actually get it to go uphill. And so it would be either sliding downhill instead, or if the velocity happens to be uphill, it has to be getting slower. As you've encountered several times at this point, the force diagram itself and the F equals ma math itself, none of that necessarily tells you which direction the object is actually moving. It can only really tell you consistently about the acceleration. And my second example, where there was friction, I did indicate the direction of motion. This time I had to specify that it was moving downhill so that you would know which way the friction vector was pointing. And so similarly, if you know the direction of the friction vector, you can use that to figure out which direction the object is moving at that moment, the moment that you have illustrated. But that's not always the case, because you don't always have the direction of the friction ahead of time. So I have rambled on a really long time, and I'm going to stop. And hopefully this was helpful.